I'm Tyler.
I'm Ashley.
And this is Matt. We did a video for our fluids mechanics class on buoyancy and stability to complete our lab 5. Enjoy.
Alright, so this is the derivation of buoyancy force based on this diagram with an object floating in the middle of water it's a square, so base and height are the same, and then there's some height between the surface level and the object. There's a pressure difference from the top and the bottom. Just going over some of the basic terms that we'll be using. So density, which is mass over volume, the density of the water. Pressure, which is represented by force over area. The pressure for the liquid is rho GH, which is that H. So the total net force on this object will be the pressure of the bottom times the area minus the pressure of the top times the area. And the top pressure is rho GH, like up here. But for the pressure on the bottom, it's the height and the distance. So it's represented by rho G times H plus E. So on this side, the net force up here, which is the same equation, but I factored out the area since the area is the same, that d by d. When factoring in the force on the bottom and the force on the top from over here, gives me this equation. And these two terms cancel out, which gives you the area, which is d squared, times rho gd, which then gives you the net force of d cubed rho g. And this is just volume. And so in conclusion, the buoyancy force is rho g v, which is density, gravity, and volume. Alright, so in this experiment we're showing buoyancy force. We're doing that by taking two glasses. One has just water in it, just a clear one, and then the other one has salt water in it, so we mix a bunch of salt in with water. We're going to drop eggs into it and show how the different densities affect the buoyancy force.
Eggs, glasses, floats, sinks. Okay, stability of a floating body can be defined as stable if the center of gravity, which is here is C, is lower or beneath the center of buoyancy, which is here as CB. The center of buoyancy is where it floats, how it floats, and the center of gravity is obviously where all the forces come down and where the center of mass is. This is our egg, drawing an egg. We can see that it does have, the center of buoyancy is above the center of gravity, so it does have a stable point when it's in it, when it's floating. Later in the experiment you'll see how when a disturbance is induced, a restoring moment happens to restabilize in its normal point. When it's sitting in equilibrium, all forces are equal. So like we've stated previously, the buoyant force is equal to the weight of the egg, meaning when it's suspended. So here in our demonstration of stability, I have an egg here with an X on the top so we can distinguish which side, end from end. So no matter how I drop this in this salt water, we use salt water again from the last explanation for buoyancies in order to make it float, because it wouldn't float in the regular water. So no matter how I drop this in here, this X will end up being at the top of the surface and this end floating. So as I drop this in here, the X will come up no matter how I orientate the drop. There's the X. Alright, thank you for watching our video for Lab 5. Just to conclude, we related the stability of the body of the egg and the buoyancy force. So the main key thing to come back out of the buoyancy force is rho salt is greater than rho egg, which is greater than rho water, which explains in our eggs here why the egg floats in salt water and the egg sinks in regular water. That's the main thing to take out of the buoyancy force. The stability of the body, the main thing to take out of it, it's stable if the center of gravity is below the center of buoyancy. To clarify, here's the picture, center of gravity below the center of buoyancy. That's how you know in our video of the X is on top. And then with the disturbance will induce a restoring moment to restabilize. So with the egg again, if I give it a flick, the X will still be on top. See, flick, flick.